The extra hidden ingredient in the theory of electron transfer rates is the so-called reorganization energy. To understand what this is, look at this electron transfer reaction here, where an iron 2 plus gives an electron to an iron 3 plus in solution to become an iron 3 plus and leaving behind an iron 2 plus. The rates of such reactions can be followed spectroscopically, for example using an isotope of iron. What is found is that there is a finite rate of kinetics for a reaction in which the reactants on the left and the products on the right are identical, and therefore the delta G for this reaction must be zero. What is the source of this kinetic barrier? To understand this, realize that an iron must have solvent polarized around it. And if the iron were to lose its charge in a system of products, so here I'm showing an iron on the left and an uncharged molecule on the right, and then here an uncharged molecule on the left as the product and an iron on the right, the polarization of the solvent has had to transfer from the left to the right, and work has had to be done in doing this since the solvent over here cannot influence the solvent over here. These changes in solvent polarization are referred to as outer shell reorganization. They may be accompanied by changes in the polarization of the molecule itself, referred to as inner shell reorganization. So how to include this solvent reorganization energy in an expression for the electron transfer rates? This is done in the Marcus theory. What is shown here is a diagram analogous to that we used for the Kramer's theory of reaction rates, where I show the electronic energy here for the reactants and here for the products as a function of some reaction coordinate. At QA, the reactants are in their equilibrium configuration, and at QB, the products are in their equilibrium configuration. The assumption is that as the coordinates of the atoms distorts owing to thermal fluctuations, it does so in a quadratic way. So I am writing down the expression for the additional energy here as 1/2 times a spring constant times the distortion squared. I'm assuming that the same spring constant applies to the system of products as to the systems of reactants in writing out a similar expression for the parabolic energy of the distorted system of products on the right here. Of course, this is not in general true, but it makes our analysis of the problem much easier. You will see that the so-called reorganization energy, the energy needed to transfer an electron directly from the reactants to the products, would correspond to a vertical transition on this diagram, at this point labeled QA here. However, the reaction proceeds via this low energy state here, in which, first of all, the reorganization energy is much less, and secondly, reactants and products are degenerate, permitting a transition by Fermi's golden rule. If we set QA equal to 0, as done here, we can see straight away that the reorganization energy must be given by a 1/2 kqb squared, because that's the height of this parabola at this point here. We further see that these two parabolas intersect halfway between 0 and qb, i.e. at qb divided by 2. So we can then write down the energy of this transition state here as a 1/2 kqb squared on 2. Noting, as I just said, that lambda, the reorganization energy, is given by a 1/2 kqb squared, we then arrive at this expression for the energy of the transition state in this simple case where there is no free energy difference between reactants and products, lambda by 4. So you see there is significant kinetic barrier to electron transfer even when there is no free energy difference between the system of reactants and the system of products. The details of how the reaction occur depend on the nature of this crossing point here. If the system of reactants and products is strongly quantum mechanically coupled, then a gap is introduced at the crossing point corresponding to bonding and anti-bonding states, and this means that as the transition state is approached, it's highly likely that the system will move from that of reactants to products. This is called adiabatic transfer. If, however, the interaction is very weak and there is no split here, then the system can oscillate up and down many times at this point before making a transition from a system of reactants to a system of products. What happens when the two systems are not in fact degenerate, as is usually the more interesting case? So I've drawn here a parabola for the reactants, assuming again the same spring constant for simplicity, but shifted up from 0 by an amount delta G0, the thermodynamic driving force for the reactants to go to the products. Now the math becomes a little more complicated. We will set the energy at this intersection point here to be equal in the expression for the parabola of the products to the energy in the expression for the energy of the reactants. And doing this then, we say that 1/2 k q squared is equal to 1/2 k q minus q right all squared plus delta G 0. This occurs at the transition state, which I'll label as Q star, and we can then solve this for Q star, and the result we obtain is that Q star is equal to 1/k QR delta G 0 minus 1/2 k QR squared. We can then plug this back into the expression for delta G, and we obtain then an expression for this transition state energy here, delta G star, as being equal to 1/2 k q star squared, which is the same as 1/k QR squared, a k not a k squared here because we multiplied by 1/2 k, put the 2 in here, times delta G 0 plus 1/2 k QR squared all squared. If we then substitute in our result, lambda is 1/2 k QR squared, putting this into this expression and simplifying, we then obtain for the transition state energy delta G star is equal to delta G 0 plus lambda all squared over 4 lambda. This then gives you a probability for a transition as shown here. I've normalized this expression for the transition state energy, now put into an Arrhenius form and normalized. An important and interesting thing to notice is that as the driving energy for the reaction is increased, the intersection point of these two parabolas moves downwards, increasing the reaction rate. However, as the free energy gets even larger, the intersection point starts to go up again, leading to a point where the reaction rate falls. This is the famous inverted region, and it was the observation of this region experimentally that won Rudy Marcus the Nobel Prize for this model. One simple model for the reorganization energy is given here, and you can see that it's simply the Coulomb charging energy for an atom of radius A, where we consider the difference in energy between an unpolarized solvent and a polarized solvent as represented by this 1/epsilon. Finally, note then the use of this expression for the kinetic barrier to electron transfer allows one to make a proper calculation of the electron transfer rates in the Averym-Ratner diode,